For this question, we're asked to find a function which gives us an injection from pairs of natural numbers to single natural numbers. That is, we want a function f which takes two natural numbers as input and produces one natural number as output. We can think of this function as having two inputs, which are natural numbers, and one output, which is a natural number. And for this function to be an injection means on distinct inputs, it takes distinct outputs. Or put another way, if I know two input pairs which make this function take the same output, well, it must be that those inputs were in fact the same. If f of x1, y1 equals f of x2, y2, then it must be the case that x1 equals x2 and y1 equals y2. So how might we find such a function? Well, there's a lot of choices, and what I'm about to present may not be the best one, but it is one simple function that does the job. We're going to take advantage of the fundamental theorem of arithmetic. Recall that the fundamental theorem of arithmetic tells us that every positive integer can be expressed as a product of primes in a unique way. And because it's a unique factorization into a product of primes, we know that, for example, every positive integer is uniquely some power of the prime 2 times some odd number, some number that has no further factors of 2 within it. The uniqueness of this will give us the injectivity we want. The function we're going to use will say f of xy is a power of 2 determined by x times an odd number determined by y, specifically 2 to the x times 2y plus 1. This function is an injection from pairs of natural numbers to natural numbers. In fact, an injection from pairs of natural numbers to positive integers. It's a one-to-one mapping, as some people say, because if f of x1, y1 equals f of x2, y2, then 2 to the x1 times 2y1 plus 1 equals 2 to the x2 times 2y2 plus 1, which means, by the fundamental theorem of arithmetic, and specifically the uniqueness of this decomposition, that x1 equals x2, because both sides have the same number of factors of 2, and therefore y1 equals y2, because once you get rid of all the factors of 2, both sides are 2y1 plus 1 on the left and 2y2 plus 1 on the right, which means y1 equals y2. So we've now found a one-to-one function that takes pairs of natural numbers and spits out natural numbers. This is not a bijection, however, from pairs of natural numbers to natural numbers, because there are some natural numbers it doesn't hit. But we can easily rectify that. The only natural number this function doesn't hit is 0. Every other positive integer will get hit by this function. That is, it will be the output of this function on some inputs, because every positive integer is some power of 2 times some odd number, again by the fundamental theorem of arithmetic. So we have now a bijection from pairs of natural numbers to positive integers. How could we turn that into a bijection whose range was the natural numbers rather than the positive integers? Well, we can take advantage of our bijection between positive integers and natural numbers. The most natural such bijection is just to shift everything down by 1. So if we just take this function and add a minus 1 to the end, it won't change anything essential in terms of our argument for injectivity. My minus 1s have been written fairly sloppily here, but I'm sure you understand what I mean. It won't change anything in terms of our argument for injectivity. Distinct inputs will still go to distinct outputs. But now we'll also have the property that every natural number is some output of this function. And so now we've found a function describable purely in terms of familiar arithmetic operations, which gives us a one-to-one correspondence between pairs of natural numbers and single natural numbers. By one-to-one correspondence, I mean we can send this function one way to turn a pair of natural numbers into a single natural number, but we can also find an inverse for this function that goes the other way. These two mappings precisely cancel each other out, so that every pair of natural numbers corresponds to exactly one single natural number by applying this function, and every single natural number corresponds to exactly one pair of natural numbers by figuring out which pair gets mapped to it by this function.